He is a senior biochemistry major at St. John's who hails from Druzy, Oregon. He comes from a long lineage of ranchers living in an Oregon county populated by more horses than humans. That town sounds awesome. He attended a one-room schoolhouse, became a pilot at the age of 15. Come on, guys. These are astonishing human beings. And graduated in high school class of 17 students at St. John's. O'Toole participated in the Roman Greco, I know how to read, study abroad program in fall of 2015. While in Athens, Thomas and 3 other students paid their own way to fly to Lesbos and help the refugees who were streaming in from Turkey. Thomas has won 2 of CSB+SJU's most prestigious chemistry awards, published a scholarly paper on modifying amino acids, served a noteworthy internship at the Mayo Clinic already, and has been accepted to medical school. He is a certified emergency medical technician, and I'm starting to think there is nothing this man cannot do. And tentatively, he plans to specialize in pediatric orthopedic surgery. Ladies and gentlemen, clearly the one and the only Thomas O'Toole. Come on.
Hello, everyone. Thank you for having me. So, I have something to talk about today, and that's NMR, which I refer to as the Chemist camera. And I hope to show you a little bit why I do that. So, I hate chemistry, which might be shocking, but at least that's what I would have said 4 years ago when I was a freshman at St. John's. I was a biology major, which meant chemistry was a requirement. And I remember one night, I was studying chemistry, sitting in the basement of Alcuin Library. This was freshman year. And I was just trying to memorize this stack of note cards full of molecules and reactions. And it all seemed so pointless. It seemed irrelevant to what I was doing. And what I realized, though, was that I asked myself a question at that point, and that was, how do we even know that this is what these molecules look like? How do we even know that this is their structure? And this question really struck me, because molecules such as these are essentially invisible. They're smaller than the wavelength of visible light, meaning that no light microscope, no matter how powerful, will ever be able to see their structure. Light itself is simply not high enough resolution to see the structure of molecules. And the more I thought about this question, the more I realized that asking it was more than just an attempt to understand the chemistry I had to learn for class. It was an attempt at understanding the world around me. Because molecules are everywhere, and they're in everything. And determining their structure is more than just an intellectual exercise. It's the very basis of modern life. Because, for example, we have our molecular understanding of biology has given rise to the medications and therapies that have enabled modern medicine. The development of preservatives, pesticides, and fertilizers have allowed us to feed the growing human population. And even electronics, such as the screens of many of your smartphones, they rely on organic molecules designed specifically for that purpose. So in essence, modern life itself relies on our ability to determine the structure of molecules. Because in order to design molecules for specific purposes, such as medications, for instance, we have to know their structure. Because designing a molecule without knowing its structure would be like trying to assemble an airplane blindfolded, where you know what it's supposed to do when it's done, and you have an idea of what it's made of, but you have no clue how the parts fit together and are arranged. So I didn't realize it at the time, but it was this question that I asked myself that night in Alcuin Library that initially sparked my interest in chemistry and in science, and it's changed my entire life as I pursued the passion for science that it provoked. So, how do we answer this question? How do we determine the structure of molecules? The answer is one of the most powerful and interesting techniques in all of science, and that is nuclear magnetic resonance spectroscopy, which might sound scary, but we can imagine it like a camera, and just like a camera takes images of objects, NMR allows us to take abstract images of molecules. And it does this using magnetism instead of light. And I'll try to describe a little bit how that works today. So, what we got here? Yeah, so first we have to know what molecules are. So this is an example of a common one. This is caffeine. You've seen it, you all see it every day almost. And here we see that each letter represents a different atom, and the lines between them represent the bonds that connect them. And it's this specific configuration and type of atoms that determines the identity of the molecule. It's what makes this uniquely caffeine. So if we could determine the organization and configuration and the relative positions of each atom in a molecule, we would know its structure. And it turns out that using NMR, we can do just that by taking advantage of three interesting properties of atoms, which, as we can see here, have a positive nucleus at the center and negative electrons surrounding it. And so the first interesting thing about atoms is that this positive nucleus, some of them are magnetic, meaning they behave like tiny bar magnets with a north pole and a south pole. So we can imagine them as tiny compass needles. And just like a compass aligns itself with the magnetic field of the Earth and points north, if we place a molecule in a magnetic field, its nuclei will also line up with that field. And so too, the second thing that's interesting about atoms is that these same nuclei possess spin angular momentum, which is another scary word, but it just means that they spin like a top, or we can imagine them spinning like a top, actually. And so finally, the third interesting thing is that surrounding these positive nuclei is a cloud of negative electrons. And when some of these electrons are shared between two nuclei, they form a chemical bond, and they form a molecule then. So as these electrons are holding the molecule together in the middle, they also form a shell around the nuclei, shielding the nuclei from feeling the full strength of a magnetic field. So this means that each nuclei in a molecule feels a slightly different magnetic field depending on how it's bonded to the other atoms around it. And if we could measure this magnetic field at each nuclei, we could determine the structure of the molecule. And I'll try to use this wheel to demonstrate how we do that. I should grab this though first. Okay. So we can imagine this wheel as a nucleus, and we have a north pole and a south pole, and we can imagine gravity as the magnetic field that's holding it in line. And so what we can also remember though that nuclei we can imagine are spinning like a top. And so here, nothing very interesting is happening because it's in line with the magnetic field. But we can tip it 90 degrees perpendicular to the magnetic field, and something interesting happens. It precesses, and this precession is what allows us to determine the structure of molecules. Because the speed at which these nuclei precess is directly dependent upon the magnetic field that we place them in. And this means that we can use an extremely sensitive antenna, much like that on your car, and we can measure the frequency with which these are spinning. And this tells us the magnetic field that each nuclei feels. And we can graph that like this, where the location of each peak represents the magnetic field felt by particular nuclei. And as you go farther left, the stronger the magnetic field. So now that we know the strength of magnetic field that each nucleus feels, and we remember that tells us how atoms are bonded to each other, we can reconstruct the structure of the molecule. So in essence, this is a photograph of caffeine, but it's taken with magnetism instead of light. And as you can see, NMR allows us to explore the invisible world of molecules. And it has enabled the existence of the modern world, where we're not limited by the wavelength of light, but by human ingenuity and innovation. It's allowed us to intelligently manipulate our environment on the most basic of levels. And for me, it's changed my entire life because of the interest in science that it provoked. And And I think that it's this complexity that NMR shows us in front of our very eyes every day. It shows the molecules that we see in our everyday life that demonstrate to me that give me the curiosity that has driven me in science. And this has led me to do research on the synthesis of pharmaceutical precursors, where I've used NMR to determine the structure of the molecules that I make. And it led me also to the Mayo Clinic, where I researched the genetics of stem cell engineering. And finally, it set me on a course for medical school, where I hope to apply this scientific interest in service to others. Yet no matter how familiar I become with this invisible world of molecules around me, I'm still constantly amazed at the complexity of their structure and the implications of that structure. Because there's far more than what we see far more to the everyday world than what we simply see. It's vastly complex and extraordinarily interesting. And it's this fine detail that drives my curiosity in science and maintains my curiosity in science. And I hope I never lose that curiosity, because curiosity engages the mind and provokes constant questions about the world around us. And I'm thankful for those questions, because had I not asked myself that one question that night in Alcuin Library, I wouldn't be where I am today, nor the person that I am today. So in closing, I'm not going to ask you to love science or love NMR as much as I do, but just be curious. Look for the extraordinary in the everyday and ask questions, because sometimes asking the right question can change your entire life. Thank you.